Just like on all the webinars, we're just waiting for people to file in. And I see the numbers are starting to go up. So I'll just give you guys a minute to get in and get settled, and then we'll get started. We'll start with a couple of poll questions, and then we'll move into the session. So once again, it looks like we've got representation from right across the country, also up in the territories. Looks like the prairies are missing from here. So I'm sure we'll get some from the prairies showing up soon. All right, I will share the results from where everybody's from. Let me just do that here. So we've got mostly from Ontario today, but we got some from right across the country as well as down in the States. So excellent. Thank you so much for answering that. I've got one more question. We like to know what your occupation is, so we know who our audience is. So let us know what of these categories best fits your occupation. And if it's not listed, then just let us know in the chat. I see somebody had posted in the chat, perhaps where they're from. So. Okay, so it looks like we've got a nice mix of a number of different occupations from the building community, the energy advisor community, engineering and architecture, government, some from academia, and we've got some utilities and suppliers on here. Excellent. Okay, so just it looks like a few more people are participating on that one. Okay, I'll just go ahead and share those results so you can see we've got a nice mix of people in all of the different occupations. So thank you so much for answering those polls. My name is Stephanie Coleman, and I work with Building Knowledge, and I'm super excited for part 2 with Chris Magwood. This is our part 2 for our carbon series that Enbridge has been sponsoring. And so Chris Magwood has joined us today, as well as Lucas Coletta from NRCan. And so just a bit of Zoom housekeeping before we get started. For any questions that you might have, just put those in the Q&A function that you see on your screen there, and save the chat for just general comments and that sort of thing. The Q&A function works a little bit better for being able to read the questions. Otherwise, the chat, it gets in a bit of they get lost sometimes in the scroll. And also too, all of these sessions are being recorded. And so I'll be sending out a resource email with the slides, as well as the links and a Survey Monkey. Now, I accidentally had forgotten to include the Survey Monkey last time, so I did send the Survey Monkey for last session in the resource email. So if you have a minute, fill that in, and I would greatly appreciate that feedback on part 1. So that is the Zoom housekeeping that I have. And so I would like to just remind you that this is a 4-part series. So make sure you register for each of the 4 parts, and you will get the Zoom links for them. And so next, I would like to introduce Susan Cudahy, our sponsor from Enbridge. Susan.
Thanks, Steph. And just on behalf of Enbridge Gas, I just want to welcome everybody who's participating today for this session 2 on carbon emissions and material selections within this 4-part series. We had a really excellent turnout for our first session. I think there's so much interest in this topic, and I'm sure we're going to have the same today. I don't want to steal any of Stephanie's thunder in introducing our guest speaker, Chris Magwood, but I just wanted to note that I'm really personally very proud of the Endeavour Centre in Peterborough, since it was my actual hometown for over 25 years. And with over 144 lakes in that beautiful Kawarthas area, there is no place that has more reason to be focused on the environment and sustainability than they do. So as Enbridge, we are very proud to bring this research involving Chris's and his team's work on embodied carbon to our builders across the province. And it is because together we are going to move through this energy transition. We're going to develop the new and the innovative options and the offerings such as solar and geothermal, renewable natural gas, hybrid heating, and we'll become a stronger province for it. So again, just on behalf of Enbridge, we look forward to having you participate and to the opportunity in the future to continue to be your energy provider of choice. So with that, I'll just turn it back over to you, Stephanie.
Thank you so much, Susan. And of course, thank you for your continued support of the industry. It allows us to have these type of opportunities of training and education. So it's very valuable to us. So for today, Lucas Coletta from NRCan is going to be giving a short presentation. And then from there, I will introduce Chris Magwood. So Lucas is a project leader with Natural Resources Canada, the Local Energy Efficiency Partnership, or LEAP, as many of you are probably familiar with. He develops technical resources aimed at addressing the affordability and construction of energy efficient homes in right across Canada. And that's, of course, something that's critically important to us in our industry. His primary focus is on the development and industry adoption of the NRCan's cost benefit analysis tool, or also called CBAT tool. And Lucas and the LEAP team work with industry to bring energy advisors, home builders, and policymakers together to trial technical resources and guidance documents, assess their usefulness, and capture suggestions for future development. And he's also been very actively involved on, along with Patrick from NRCan on the carbon tools. So I'm going to stop sharing my screen, and I'm going to hand the floor over to you, Lucas.
Great, thanks so much for that, Stephanie, and good morning, everyone. To get my screen up and going here. So thanks for that intro. And yeah, my name is Lucas Coletta. I'm here from NRCan. I work with the LEAP team, and I'm just going to take a few moments of everyone's time at the beginning of this presentation to talk a little bit about the material carbon emissions estimator that NRCan has partnered with Chris and the Builders for Climate Action to develop and to raise awareness around embodied carbon in materials that are being used in the construction industry today, and what we have to look forward to in the future. So LEAP, as Steph mentions, stands for Local Energy Efficiency Partnership, and it is essentially a process that accelerates home builders' innovation toward net zero and low carbon projects and construction for housing. And historically, builders have been quite responsive throughout the process. I think they found a lot of value in the information that gets shared, the way networks and connections are formed, and ultimately coming out of the process with a better understanding of how to take on more energy efficient or more progressive projects in that sense. And so builders have used LEAP to reduce both their time and risk. They've also used it to take federal research results and inform some of that decision making. And some of that is both on energy conservation measures, as well as best practices towards resiliency, durability, and what we're talking about here today, embodied carbon. And alternatively, they also pool their buying power. So regionally, they come together, builders, and are able to identify technologies that their specific market would like to take on and adopt, and find ways of bringing that to their marketplace in a cost-effective way. The LEAP delivery model is 4 different steps. So step 1 is our planning workshop, where we select different technologies that builders deem are valuable to them and to their everyday business practices, as well as ones that we'd like to explore moving forward. So new technologies that might be coming into the market that may be more cost-effective or maybe more efficient. Step 2 is taking those learnings and sharing them in a forum. And so this is where we can do an apples to apples comparison of manufacturers who have brought these technologies to the market and are showing builders how they could take these technologies and apply them to their construction and builds. Step 3 is trialing this information and trialing these technologies. And so we use the trialing mechanism to unlock market change. This is kind of the early adopters or the pilot projects, where we take state-of-the-art technologies or ones that are a little bit less widely adopted and support builders in learning how we can implement these, whether it be heat pumps, solar panels, all these different energy conservation measures, so that others can take those learnings and hopefully go through the process in a quicker and less less risky way, I would say. Step 4 is developing knowledge materials and guides. And so, like I mentioned, the embodied carbon calculator that we're going to talk about in a moment is one of those tools that builders can use to take research results, to take pilot project learnings, and be able to apply some of these in their own houses, in their own designs. So NRCan's Material Emissions Estimator, it's called MCE squared. So this calculator, it's designed to support the home building and renovation industry in making informed material choices to reduce upfront carbon emissions. We understand how increasingly important it is to look at the whole home outside of just its operational energy. Look at the materials that we're using, and taking that all the way back to all the different cycles through that product's life, whether it be extraction, transportation, or manufacturing in this case, and understand how our decisions are ultimately impacting our overall goal of wanting to reduce carbon. So by combining our operational energy data from HOT 2000 with estimates of the project's upfront material emissions, users will be able to review a plot of the cumulative carbon footprint for their home and renovation projects. So this tool is aligned with HOT 2000. After a HOT 2000 model is created, you can port it into the carbon estimator, and it will present you a variety of different material options, as well as the carbon emissions associated with each of them. And the idea is to help you make more informed choices about the materials you're selecting, and again, ultimately the impact on carbon that they will have. So the NRCan Material Carbon Emission Estimator, it's going to be available in late November to early December. It'll be published on the LEAP website. And if you have any questions about that, or want to learn more about the LEAP carbon calculator, feel free to reach out to either Chris or myself or Steph, and we'd be more than happy to provide you with the information that you're looking for. So I think with that, I'm going to wrap it up, and we have a couple of poll questions here that we'd like to get everyone's feedback on, just as we roll into this presentation from Chris. So the first one is low carbon desirable to home buyers?
Like we got a quick question in the chat while we get these results here. Is this similar to the EC3 embodied? Oh, it disappeared. Where did it go? Embodied carbon calculator, or how is it different? Do you know?
Maybe I'll let Chris answer that. Chris, are you familiar with the EC3 calculator?
Yeah, I am, and I'll sort of address that maybe in more depth, because I'm going to sort of go through the tool and how it works and what it's for. But it's pulling from the same kind of pool of data, but this one is specifically designed for low-rise residential construction, and is sort of made to model particular buildings, whereas EC3 is more of a database where you can find the source emissions for all of the materials, but it doesn't sort of help you with the calculations to figure out, what the impact of that would be for your particular building. So the MCE squared tool is kind of takes that step out and makes it easier for somebody specifically in the low-rise residential field to be able to use that information.
Great,
Thank you. So here are the results. Lucas?
Yeah, so it looks like 61% of folks think low carbon is desirable to home buyers, which I think it's great that more and more folks are becoming aware of how their choices are impacting on carbon. So that's great to see. And we'll keep going on to the next question here. So the next one is, as I change my screen, would you change your construction specs to reduce upfront carbon emissions?
Just waiting for a few more respondents. They keep coming in. All right, so I'll share these results here.
Okay, well, it's excellent. we're glad to see that folks are open to change. And I think as we learn a little bit more throughout today's presentation about the embodied carbon of different construction materials, we might even see that there's more energy or more cost-effective opportunities to reduce carbon through those decisions as well. So thanks everyone for participating in this poll and these questions. And again, if you had any questions about the MC squared calculator tool, feel free to reach out to us, but I'll leave it there and turn it over to Chris.
So thank you so much, Lucas. And thank you, Chris, for chiming in there on that question. I'm sure we're going to have lots of questions. So I wanted to introduce Chris. Chris is, I like how he's worded it. He is obsessed with helping reverse climate change by making carbon storing buildings that are also healthy, beautiful, efficient, and inspiring. Those sound like fantastic buildings to live in and work in, Chris. Chris's background is in building, having co-founded Camel's Back Construction in 1998. And that was a design build firm that focused on straw bale construction and renewable energy. So in 2011, he's been a director and a teacher since 2011 at the Endeavor Center that Susan had mentioned earlier. And that's a not-for-profit sustainable building school. That's in the Peterborough area. In 2019, he helped to establish Builders Climate Action and has been leading development of the BEAM carbon estimator tool for low-rise carbon construction. And he's working closely with many levels of government to develop the embodied carbon benchmarks and regulatory programs. And of course, helping builders and developers figure out how to reverse climate change with the buildings that they construct. He completed a master's degree at Trent University and published his thesis, which was called Opportunities for Carbon Removal and Storage in Building Materials, and that was back in 2019. He's an author of 7 books on sustainable buildings, and you have a new book coming out, Chris, so that sounds great. It's called Building Beyond Zero, New Ideas for Carbon Smart Architecture, that he's co-authored with Bruce King, so that's coming out at the end of this year, I believe. Or maybe released very soon. I'm sure you can let us know. And you are also, as I know and have had the privilege of being able to work with you on multiple workshops, you're an active speaker and a workshop instructor, both in Canada, but also internationally. So once again, I'm thrilled to be working with you together, Chris, and I'm going to hand it over to you.
Okay, yeah, thanks so much for that intro. And thanks everybody for taking the time to be here today. It's great both to see the number of people that have showed up and the results from those poll questions were really encouraging. And I just want to thank Enbridge and Building Knowledge for the chance to bring everybody together today and be able to have this time with you. So this is part 1 of my presentation, and this one is sort of focused more on kind of methodology and tools. And the next session, we're going to actually look at some case studies and get more into, what materials have what impact and looking at some specific buildings. But today is to sort of set the background and kind of, as the title here says, let you sort of know what the state of the art around understanding material emissions is right now. It's definitely a newish field. And it's still a work in progress, but we'll be able to show you kind of where things are now, what we do know, what we don't know, and how you might be able to put that to use. So anybody who was at the previous session that Steph presented at has seen this graph, or you might have seen something like this somewhere that, this is specifically for Canada, but that buildings represent about 30% of emissions. And we want to make sure that we're not just counting operational emissions in that take, but that we're figuring out where building materials show up in lots of these other categories. So obviously, it's fairly easy to measure both energy use and then emissions from operating buildings. But the manufacturing of the materials is kind of buried in a lot of these other categories. Some of the oil and gas that's extracted is for building materials. The electricity is used for that. Transportation is used for building materials. And that heavy industry bar includes the manufacturing of a lot of materials. So we're kind of thinking now more about the full life cycle of our buildings, and that's where this whole notion of embodied carbon as sort of distinct from operational carbon comes in. And you may have seen various versions of this sort of life cycle graph where something starts as raw material, gets transported to a factory, is made at the factory, gets transported to a job site, is put into a building. That's kind of the upfront embodied carbon. So those parts of the life cycle involved in sort of making the building. Then while the building is in existence, there's the operational carbon that we have been focused on, most of us in the building industry, for quite a while now. And then there are further life cycle impacts from those materials in those buildings in terms of maintenance and refurbishment and repair, and then finally sort of the end of life of a building or the products within the building. So most of the people who are attending today are probably very aware of the operational carbon piece, and we've all been putting a lot of great effort into reducing that, both by making buildings more airtight, more insulated, improving mechanical systems, and looking at the types of fuels we're using for those buildings. But the work that I'm going to talk about today is looking at the impacts found in this upfront piece, and in particular, the chunk that's highlighted in red, which is sort of the product phase of actually manufacturing the materials. And the reason the focus is there is because this is where the highest chunk of material life cycle impacts happen, is in this product phase. In life cycle assessment, we call these phases A1 to A3 for raw material supply, transport, and manufacture, more sort of colloquially known as cradle to gate. And the reason for focusing here is this is where the bulk of these emissions do happen. So 70 to 85% of a material's impact is going to be here, but also because the most reliable data on those emissions lives here, because we can sort of go to manufacturers who understand kind of their whole supply chain up to the point where the product leaves their gate. Those are quite easy to quantify, whereas when we get into transportation to site and construction impacts, those can vary really widely. Not that they're not important, but they are a much smaller piece of the overall pie, and they vary depending on each person and each building. So we have chosen for this work to really focus on this cradle to gate phase. And we get all the information about that cradle to gate phase from reports called environmental product declarations, or EPDs. And I apologize, as we get into this, like any subject matter, the sort of carbon emissions world is full of acronyms, and I'll try to spell them out and not use them without explaining them first. So an environmental product declaration is a report on the impacts of different types of products. These EPDs exist for all kinds of products, not just building materials, but for building materials, there are particular categories. So, flooring is looked at through a different set of product category rules than insulation or concrete, or, like materials are kind of treated in similar ways. But this international standards organization kind of standard sort of says what you count and what you don't count and how you go about counting it. And then they're either made by or verified by a third party beyond the manufacturer themselves. And so this gives us, one of the pieces of information that an EPD gives us is the global warming potential of that material. So that's a figure that says for a certain quantity of that material, a certain amount of emissions go into the atmosphere. And those emissions are sort of all put in terms of carbon dioxide. So there might have been, fluorocarbons emitted, there might have been methane emitted, there might have been CO2 emitted, but the number, the GWP number is given so that all of those emissions are in what's called carbon dioxide equivalent. Like I said, EPDs are third-party verified. So there are program operators around the world who both create and or verify EPDs for manufacturers. These are some of the more common ones that you'll see, but they are sort of ensuring that the quality of the data and the comparability of the data is there. And so, you know, that sort of, when you're looking at an EPD that has been third-party verified, you have, you know, a pretty good degree of certainty that you're working with information that's reliable and comparable. It's also important to know that there are two kinds of EPDs out there. Some are industry-wide, so you will have an industry organization that gathers information from all or some representation of its membership, so that what you're seeing is an average for the emissions that come from a certain product from, you know, a wide range of manufacturers. And then you have sort of manufacturer specific or even product specific EPDs where it's one particular company's emissions that you're seeing in their EPD. And it's important to sort of be able to distinguish between these because, you know, an industry-wide EPD, it's going to give you a number that is a reliable average, but it sort of means that the number you're using for your building may not be accurate to your location. So for example, the same factory making a material using a lot of electricity in a region where the grid is mostly supplied by coal will have a much higher climate impact than the exact same manufacturing process using the same amount of energy, but if that electricity is coming, say, from all renewables. So if you're getting the product from the coal-fired plant instead of the other one, you might think that the emissions from your material look like the average, but they may actually be much worse than the average, or they may be much better than the average. So, you know, whenever possible, it's really great to get manufacturer-specific and product-specific EPDs. Like the wording says here, it really helps with procurement if you want to be able to compare, you know, product A to product B, even within the same category. Then we need these product-specific EPDs to be able to do that. So I've mentioned this a little bit, but kilograms of carbon dioxide equivalent is the way that global warming potential is typically expressed. And this is just sort of explaining that different greenhouse gases have different warming impacts. So carbon dioxide is sort of given a global warming impact of 1, and then, you know, different greenhouse gases could have a lighter or heavier impact on the climate than that. So methane is equivalent to 34 tons of carbon dioxide, or a ton of nitrous oxide is 298 tons of carbon dioxide. So we put all of that together in EPD language, and as we talk about material emissions as kilograms of carbon dioxide equivalent, so that we have one metric that we're able to use, even if all the emissions aren't carbon dioxide. So the quick and easy explanation of how you take all of that EPD information and figure out the carbon footprint of the materials for your specific building would be, you find all of the EPDs for the products that you're going to use in the building. You do your own material quantity takeoff, and then you multiply your material quantity by the global warming potential per quantity in the EPD, and that will give you the carbon footprint of a particular material. And then you do that for each material, and you add them all up, and then you'll get your whole building material emissions from doing that. So, you know, to do that on a building by building basis, it takes a lot of work. The first time I calculated a building, it took me about 1.5 years to find all the EPDs and to do all the background calculations. So clearly, you know, that was a longhand way of being able to understand the material impacts for one building. So before I go on to the tool that we've developed to kind of do that for you, I wanted to just pause and take any questions that have come up from that sort of background explanation before we wade any deeper.
So I'm just looking here, and it doesn't look like there are any questions on that part yet. But maybe, are you going to be talking about what components of a home have EPDs versus ones that maybe don't have EPDs, or how you deal with all of that?
Yep. Yeah, that's kind of coming next. So
perfect. Okay, so actually a question did just pop in. It says, how much does it cost for a manufacturer to get an EPD? Do you have any information on that?
A little bit. That, you know, that's not something that I do, but from talking to manufacturers, I've heard that it's anywhere from sort of $10,000 to $40,000, depending on you know, the extent of the operations, how much data is already known, how long the supply chain is. You know, there's a lot of factors that go into it, but the numbers I've heard are sort of in that range.
Actually, I'll add on to that question. Do you have an idea of how long it takes for a company to go through that process? And then there was a further comment that was asking, you know, how do we convince people that it's worthwhile to actually do the EPDs? Right.
I will take the second question first and say that, you know, I think just reaching out to manufacturers and requesting it is really important. You know, they often they don't have any sense of how important this is to their customers, but they, you know, most companies are pretty sensitive to customer requests. And so the more they hear that, oh, our customers would like an EPD, the more likely they are to do it. And I think, you know, we're at a point now where enough companies have sort of done this of their own accord that the data set is pretty good, and the sort of learning that comes from looking at that data set is driving companies to change products, improve their processes. So many times now, an EPD has a shelf life of 5 years. So many times now, I've seen that the next EPD that comes out from a company there's a significant improvement in the carbon footprint. It's been lowered quite a bit, and so, you know, like with all things, once the numbers are out there in the world, you know, manufacturers want to have good numbers. They want to show up well in the marketplace. So encouraging people to do that more is really important. I think in terms of the length of time, again, it depends a lot on the complexity of the product. So you basically have to look at all of the inputs through the entire supply chain. So if you have a very simple process like cellulose insulation, like I get the paper, I grind the paper, you know, I add the fire retardant, I put it in a package, you know, that's fairly simple to do. If you're, say, a manufacturer of a heat pump, and you have, you know, maybe 50 different materials in there that all come from different suppliers. There are different places where different parts of those are assembled. Like, you have to figure all of that out backwards along the supply chain, so that the length of time and complexity depends a lot on the product. And then, you know, on how much both the company itself and its suppliers already have that information at their fingertips. You know, for some companies, they're already tracking that stuff. So when somebody comes to do an EPD, they just can hand them all the right information. Other companies may not have been tracking any of the stuff that an EPD maker needs. So they would have to kind of build that up from scratch. So it's a pretty variable process in a lot of different ways.
Mm-hmm. And so something that I had talked about last time was the pressure, you know, that industry is beginning to start to feel from all sides, whether it's regulation or other, but it could be even from internal. And I gave the example of RBC that requires some of their supply chain to voluntarily report their emissions. So we could see more of these EPDs coming up as more pressure comes from different sides, I'm sure. Now, there are a number of additional questions that have come in. However, I want to make sure that we don't go too over on your time. So do you want to take some more questions, or do you want to hold these ones until a little bit later?
Yeah, maybe I'll wade in because then the next section is going to sort of still be talking about a lot of that data related stuff. So some of it might get answered, and if not, we can take them at the next pause.
Okay, that sounds great.
Okay. Whoops. Okay. So when you get EPD results or results on a whole building emission analysis, people, the sort of most common question I get is like, what have I learned? How accurate is this? What am I actually seeing? And I compared the process a lot to fuel economy estimates, where there's a particular set of instructions that a car manufacturer follows to do fuel economy estimates. The car is driven, in a certain temperature for a certain distance with so many stops and starts and at a certain speed. And, there are all these parameters set to make sure that these things are comparable. And so, when you look, there's two fuel economy estimates on the screen. You don't necessarily think that when I get into that car, I'm going to get exactly 18 miles to the gallon or 29 miles to the gallon or, whatever it happens to be. But what you do know is that when you look at it in this particular way, you can see that, gee, a car with a V8 engine uses a lot more gas than a 6, which uses more gas than a 4, which uses more gas than a hybrid. And I would say that's the sort of level of resolution that you can get really clearly from the kind of work that we're doing now. So if I tell somebody, their building has a carbon footprint of 18 tons, I don't mean that it has like literally, 18 tons of emissions associated with it. It's not that, the resolution is not that fine. But if my answer, for one version of the building is 18 and we switch out the materials and we do one that says it's 12, we know that we've done a fairly significant effort at reducing the carbon footprint of that. And I would also say, when we get into the tool that I'm going to show you, think of it a lot like an energy modeling software. When you see an EnerGuide score that says, oh, this house is going to use 61 gigajoules and this one's going to use 236. If you check the energy bill of that house, it's probably not exactly 61 or 236. But, again, if you sort of use the software, use the parameters, and that, if you started with a high number and then you improve the windows and improve the amount of insulation and improve the air tightness, you're going to get a better number. So, these are great for comparisons, but I wouldn't, they're not exact predictions of the exact amount of emissions. And that's why we use the term estimator with the tool. So one last thing that I want to address before we get into the tool, because I think the emission side that we've talked about so far, where you sort of count emissions and the number goes up as you add materials, makes sense. But there are a range of materials within these estimator tools that show negative numbers. And so what I want to do is just sort of be clear on what the negative numbers mean and how that works. And currently in the tool right now, the only materials that have negative numbers are plant-based materials. There are ways that people can draw carbon dioxide out of the atmosphere and mineralize it, but none of those are sort of commercially available right now. But the way this works for plant-based materials is that every plant that grows through photosynthesis. So it's literally pulling CO2 out of the atmosphere to grow. It keeps the carbon atoms from that CO2 within the plant structure, and it lets the oxygen go. And so the plant has done the thing that the IPC says we need to do, which is pull carbon dioxide out of the atmosphere. But on a regular sort of cycle, plants pull CO2 out of the atmosphere. The plants are then either eaten or burned or rot, and that carbon goes back to the atmosphere as CO2. When we make a building material out of those plants, what we do is sort of interrupt that cycle, and we put it in a building for however long a building might last. One would hope at least 40 years. One would, try really hard to make buildings last hundreds of years. But for whatever length of time, that carbon that was just in the atmosphere is now stored in the building. It's not back in the atmosphere driving more climate change. And so the amount of carbon held in that plant, expressed as an amount of carbon dioxide, makes for negative numbers for some plant-based materials in these estimations. So some people might have seen, results like this from some of the early studies I did, where certain buildings have positive number emissions and some have negative number emissions, and that's literally if you are using more of the plant-based materials, you can overall affect a sort of net negative impact on the climate. Now, the tools right now don't include any amount of carbon storage or sequestration from wood or timber related products. And that's because the climate accounting for timber products is a lot more complicated than for either agricultural residues or other sort of waste stream fibers or even purpose grown crops for building. Because anything that's sort of a sort of annual crop that's grown, we sort of understand, what that land is already being used for. It's being used to grow food, or maybe it's being used to just grow building materials. But it's going to continue to be used for that for some length of time. And we know that the carbon dioxide drawn down one year is going to be approximately equaled the next year as that land continues to be used. Forests are a whole different beast, where the entire forest ecosystem is a really important carbon stock for the whole globe. And the work that we do to sort of pull trees out of there can either help that forest carbon stock get bigger, in which case we are doing something good for the climate, or it could make the forest grow smaller and the carbon stocks in the forest grow smaller. And so simply transferring a bunch of carbon atoms from a forest to a building isn't necessarily good for the climate. It could be good for the climate or bad for the climate. And right now we just don't sort of have the sort of tools or knowledge or data to know when that's happening. And so what we really don't want to do is say wood is good, wood stores a lot of carbon because there's a lot of carbon atoms in that wood, when all we're doing is making a lot of wood buildings, but shrinking the carbon forests or the forest carbon stocks to the point where they're no longer doing this important global work of drawing carbon out of the atmosphere. So you have to remember that when you cut down a tree, somewhere around only 50% of that tree will make it into a building. So a bunch of the carbon has been released to the atmosphere, either as slash or as fuel for the mills. So at best, the carbon in the building is only equivalent to what's gone back to the atmosphere. So that's kind of a neutral. If a whole bunch of carbon that had been put in the soil by those trees comes out during that process, then there's a bunch of extra emissions that would count against the storage in the tree. If you cut that tree down when it still had 20, 30, 40, 50 years of life to keep absorbing carbon, we have to account for that. So because it's so complicated to figure out, and because nobody has really come up with a system for doing that yet, we're currently not counting carbon storage in wood products. Okay, quick pause here, because sometimes that sort of can trip people up, the notion of sort of negative emissions. So I just want to make sure that people feel clear about that.
Thank you, Chris. So there are some questions. So some from the last segment, and I'll ask those. Do the EPDs report on environmental impacts other than greenhouse gas emissions?
Yes, they do 7 categories of impacts. So they also look at eutrophication, acidification, fossil fuel use. So there are 7 in total. So that the global warming potential is just one of the 7 impacts that they record.
Thank you. The next question is, do you know if similar work is being done on embodied carbon for the infrastructure industry? And specifically, they're asking about the electricity transmission and distribution industry.
Well, that cracks the lid on a big can of worms. So the easy answer is no, not really. And a lot of this gets into the whole notion of boundaries. Where do you say we're going to start counting related emissions, and where are you not? So, currently, when you look at energy supply, we're just looking at the direct emissions from that energy, but we're not looking at what did it take to make the wires or the pipelines or the pumps or any of that stuff that delivers it. We're also not looking at the shipping involved. When a tanker truck of gasoline goes from one place to a gas station, none of that is counted. So in infrastructure right now, there's a lot of work being done on trying to identify what should we be including. But currently, no, it's not we're not sort of looking at it through a wider lens like that.
Thank you. The next question is, do you have a sense of whether cradle to gate emissions would still make up roughly 75 to 80% of embodied carbon emissions in remote jurisdictions? They're trying to get a sense of how much of an effect the higher transportation emissions to get materials to site would make when calculating the embodied carbon.
I was surprised when I did a deep dive into a few of our projects and really looked at those transportation emissions, how small they were compared to the manufacturing ones. That said, I was looking at that for projects here in Peterborough. So things, sometimes something was being shipped from Europe, but it depends a lot on how things are moving, right? Things can go halfway around the world by container ship for a very light carbon footprint, or they could go, halfway across a province in a small truck and have quite a large carbon footprint. So the sort of more remote, when you get into sort of fly-in situations, obviously, those transportation things would go way up. But in general, I was really surprised to find that, even when we were looking at cases where we were bringing materials in from Asia or Europe, that there was still a relatively small fraction, and that the manufacturing emissions far outweighed even the things that had to travel quite a distance. But I would sort of encourage people to, not take that as license, like, I'll just get anything from anywhere and never think about it, because it is important. And as you start getting lower and lower carbon footprint products, that proportion of, the transportation is going to appear bigger and bigger. So to the point where, when I've got a potentially carbon storing material, but I ship it all the way across the world, I may have just eliminated all of that carbon storage and given the material a carbon footprint that might still be better than a really high emissions material made locally. But I think, when you're sort of trying to make calls about really big differences in shipping, you'd want to take that into account.
Right. So it's really about systems thinking and looking at all the different the facets. One other question that came in was, and you're familiar, I'm sure, with some paint products that absorb CO2. And so the question is, do paint products that absorb CO2 count?
Yes. So EPDs do look at sort of like all the sort of inputs and outputs of a product. So the kind of paint, you're probably talking about a lime-based paint, and the EPD for that will include the reabsorption of that CO2. The thing to remember is that what that paint is doing is absorbing CO2 that was driven out of the limestone in the production of it. So it's not a negative emission, it's reabsorbing some of the emissions that happened when it was made. So it's not going to be a carbon storing product, but because it's going to reabsorb some of the CO2 that was emitted when it was made, it's going to have a lower carbon footprint than a comparable paint that doesn't do that. And that's one of the reasons that cement, the binder for concrete, is such a high emitting material. Is not only do you have to burn the limestone at a high temperature, so you've got a whole bunch of fossil fuel emissions to do that, but what you're doing is literally driving the CO2 that was embedded in that limestone into the atmosphere. But concrete doesn't reabsorb very much of that CO2 at all. None for the first little while. Over hundreds of years, it reabsorbs a fraction of it. But the lime paint is doing that on a shorter cycle. So within a few years, it will have reabsorbed a fair percentage of the CO2 that was driven out of it, but none of the fossil emissions that happen to make the CO2 drive out of the rock in the first place.
Yeah, it just shows the complexity of this, right?
Yeah.
So one last question, and it is, how does this work for wood-based products in buildings that are not timber? So wood composite siding, OSB, that sort of thing.
Yeah, so same thing right now. What we're doing is the EPDs for those products are calculating all the emissions attributed to those materials. So from, the removal of the tree through the whole process of both, preparing the wood and the glues or other materials that might be in that product. So all of those emissions are being counted, but there's no credit being given for the carbon atoms in the wood. It's not being attributed with any carbon storage. That's not always the case. You'll find some life cycle assessments, often ones that are trying to really make the case, especially for mass timber, that will show the carbon storage in the wood by counting the carbon atoms, the weight of the carbon atoms in the wood. I think that's a bit disingenuous at the moment, because it appears to be saying that wood is this remarkable solution for the climate, but I think without being sure that we're not doing more damage to the climate than good by putting wood in buildings, we really shouldn't be attributing that.
So those are the questions for now.
Okay, great. Thank you for those, everybody. So the way that we sort of look at this for a whole building, I sort of showed you that you kind of, add up the amount of emissions for a particular material in a building, then you add up all the materials. And what that gives you is what we call the total material carbon emissions, or MCE, and that's usually expressed in tons of CO2e. So that's like all the emissions associated with the materials in that building. And that's a good number to have. But we also will take that number and turn it into a material carbon intensity, or MCI, which is simply the gross emissions divided by the floor area of the building. And so we'll see that referred to as kilograms of CO2e per meter squared. And the reason for doing that is it sort of allows for a bit more comparison between different types and sizes of buildings. Like obviously the total emissions from a very large home are likely to be higher than the total emissions from a very small home, if you're using the same materials. But it might be that if you use a different materials palette, the big home could have a lower carbon intensity per square meter than the small building. So you'll see as we start looking at some of the results a little bit this week and more in the follow-up session, that MCI, or kilograms of CO2e per meter squared, is a really common way to express the results. Oops. Okay, so now we'll kind of get on to the tool. So MCE squared is a spreadsheet-based tool that kind of has a back end with all the available EPDs for residential construction embedded in it. It is linked to HOT 2000. So you can see the big green button here, which will import HOT 2000 data. So what you'll get out of HOT 2000, out of your HOT 2000 file, are these energy consumption numbers, which will calculate out operational emissions. And then some of the building geometry will come through too. So anything about the size of the building that HOT is able to export, that will happen too. And so you can sort of build a model here in the same way that you do in HOT or other sort of building modeling softwares. So within the estimator tool, we sort of give these handful of not warnings, but explanations about what it is that you're seeing in the tool. And the first is that we've gone to every length we can to find every available EPD for building materials, but they come out all the time, so there might be new ones that aren't in there. Also, there will be types of products or manufacturers that aren't represented because they don't yet have an EPD. So if you start using the tool and you're wondering, like, why isn't this or that included here, it's simply because either the data doesn't exist or it began to exist after this version of the tool was put together. So we will constantly update that tool with new EPDs, but it right now doesn't represent sort of every single material that you could use. What it does do very well, though, is represent all the categories of materials. I don't think there's any kind of typical materials or even sort of more esoteric materials that you might put into a building where at least one manufacturer specific or one industry average EPD isn't in there. So you'll always get a ballpark of what a particular material might be, but you definitely won't be able to sort of compare every single manufacturer of a given product just because that it doesn't exist yet. The other thing to note is that the calculations we use might not reflect all of your practices. We've tried to make this easy for people to use so that you don't have to do the material takeoffs. We're kind of doing the material takeoffs behind the scenes, but what that means is we're making some assumptions on, framing. So you can choose whether you're using, 16 or 24 inch on center, but we're making a bunch of assumptions about, total wood use. We're making assumptions about, a number of things that you would have to do when you're sort of doing a material takeoff. So what you can be assured is that the calculations we're using would give you the same results for competitive materials. So if you're looking at wood framing versus metal framing, we're using the same math to figure out how much of that you would need. So you'll get a comparative answer, but again, it might not reflect your exact practices. Part of that is that no waste factors were included. So we know that people order more material than goes into their building, but we didn't sort of make any assumptions about how much. So all our calculations are based on the exact geometry of the building with no waste factors included. I think 4 here is a really important one. Right now, what we're looking at in this tool are all the main structural elements, enclosure elements, and main finishes in the building. So we're not including any mechanical, electrical, or plumbing materials. So your heating equipment, your ductwork, your wiring, your pipes, and your plumbing, none of that's in there. The fixtures aren't in there. Smaller components like flashing, sealants, barriers, et cetera, are not in there. Appliances aren't there. Millwork is not there. Stairs aren't there. Paints aren't there. There's sort of different reasons for each of those not being included. Mostly it's because the data doesn't exist yet. Very few of the sort of mechanical, electrical, plumbing materials have EPDs. Some of them are just fairly small, and some of them we thought, the data set's limited, and also you're not really going to change your mind if we tell you, well, your poly vapor barrier has a carbon footprint of X. That's what you're going to use anyway, whether you know that information or not. So sometimes we're just trying to streamline the process because change wouldn't really be driven by knowing the answer. Again, it doesn't include getting the materials to your site or whatever emissions you have on your job site. And it doesn't include the end of life emission. So it really is looking specifically at that cradle to gate phase. So sort of knowing all of that and going into the tool, the way it works, I've kind of taken these snapshots from along the bottom of the spreadsheet, but it begins with a user input sheet where you kind of define the building. If you have a HOT 2000 model, a lot of that information will come across from HOT, but otherwise we're asking you mostly for gross building dimensions, area of exterior wall, area of interior wall, floor area, roof area, window area, things like that. We tried to really minimize the number of inputs required. And then basically it's organized by building assembly, and each one has its own tab within the tool. So after you've done the user input, you would move to footings and slabs. You'd get to the footings and slabs page, and it'll have, concrete options and pier options and, wood foundation options and insulation options, and sort of all the components that you would use to make footings and slabs, and again, foundation walls, the heavy structural elements like posts and beams, exterior walls, or we included a section for exterior wall systems for things like SIPs and ICFs, party walls, cladding, windows, etc. You kind of basically go through the tabs and build the building. And at the end, there's a page that shows you sort of all the materials you've chosen. So you can kind of do a quick review and make sure that you've captured everything. And then a results page and a page that allows you to kind of run multiple scenarios on the same building. So those are the kind of tab options. And then what comes next here. So this is a look at a part of the exterior walls tab. So exterior walls would include framing, sheathing, those sorts of things. This is the cavity insulation section. It's just part of it. I chose this one because for some of these materials, there's an additional input. So for framing, you would give us your framing spacing. For insulation, you're giving us your R value. For things like concrete walls, you're giving us the thickness of the concrete. So you sort of make those choices. And then for each category, so here's cavity insulation, you sort of get to see both the average. So in lighter blue here, all the fiberglass bat options that we have are averaged out. And if there are manufacturer specific ones, then we'll sort of call them out, and you can sort of see brand by brand how they compare. But the thing that I think is really great about the tool is that, because I've already put in the size of my exterior walls, so you can see in this case, it's 127.6 square meters. I can already see the carbon footprint of all these different material options before I start making my selections. And I think this is the sort of key to making this tool really useful, is that either between different material types or even within a specific material by brands, I can sort of say, oh, look, it's, the carbon footprint of fiberglass bat is actually lower than fiberglass, blown in, or, I could choose this manufacturer over that manufacturer, or I could go, oh, look, cellulose has this big negative carbon footprint because it, it stores more carbon than was emitted in making it. So, right away you get to sort of see what all the results would look like, and then you can start making your choices. This is the continuation of that cavity insulation thing. It's one of the places where there are a lot of options. So you can kind of see that the range is really wide from, for this building, 9,000 kilograms of emissions if I use HFC spray foam, to potential storage of 5,000 kilograms if I use straw bale, and basically, everything in between. So the idea is, the tool will really sort of help you understand, the impacts of different material types, and get you to sort of, hone your design in on the things that, A, meet your carbon footprint goals, but B, also meet all the other requirements of your building. And, by no means is this tool sort of intended to be any kind of building guide. It's really just the carbon footprint of the materials you need to know. Can you get it? Is it affordable? Is it appropriate? Are there building science issues? Like all of that stuff is left to the very smart designers and builders in the room. But we want to be able to give people that really critical piece of advice around the carbon footprint. So once you've gone through all of those tabs and you've selected all of your materials, over here on the left, I know you can't actually read that, but it's not important to read it here, is your review tab. So when you get to this point of the spreadsheet, it sort of color codes which tab the materials came from. So you can both scan it to make sure you didn't miss anything or that you didn't duplicate anything. You can scan the carbon footprint thing here to see, the orange bar is showing the things with the highest carbon footprint. The green bars are showing the parts with the highest amount of storage. So you could sort of hone in and say, oh, like, this foundation wall was my my biggest carbon footprint? Can I go back to that tab and do anything to improve that? So the review tab, I think, is really useful. You can also start to put up different scenarios for the same building beside each other and compare that way. And then you also get this results tab that will show you the material emissions here in these blue squares as both a total, so total material carbon emissions is 4 tons, or this particular building that translated to 18 kilograms per square meter. And same, the operational emissions will come through. I think because it had a decimal place, it doesn't actually capture it here, but 9 tons of emissions over 30 years. And the graph at the bottom is kind of showing you, the material carbon emissions are this blue line. The cumulative operational emissions are the black line. And if you follow the red dotted line, over 30 years, 12.8 tons would be the emissions from both operations and materials. So you get a bit of information in here, and your result will show up also on this slider bar to give you a sense of, where in the sort of range of buildings that we've seen to date, your building might fit. So I'll pause there because I'm guessing that there probably are some questions about the tool. There will be more instructions and more training available on the tool when it's released. But that was a sort of high level overview of kind of what it looks like, what the inputs are, and what kind of information you'll get out of it.
Yeah, exactly. And it's great. It's giving some really useful information, and it's designed in a way that that takes something that could be really complicated and makes it much more manageable. So there was a couple
That's what happens
questions.
when a builder builds some software. It ends up working well for builders.
That's the
I
trick.
needed it to work for me first, and so it turns out that it seems to work for a lot of people because I was really applying a builder's lens to it.
Oh, that's perfect. Well, it makes it very practical. Exactly. So, so now we're gonna have a big influx of builders moving into software development.
That's right. Yeah.
Probably not a bad
don't
idea.
do it is something that I would say. Free advice. Yeah.
That's funny. Okay, so a couple of questions did come in. So the first one is, so the kilograms of CO2 values here are different from the EPD values. Are these total values for the quantity used in the building? So I think maybe there's just some clarification on what was shown in the EPD versus the numbers that were shown in the tool.
Yeah, so the EPD gives you, and this is the reason why EPDs can be hard to work with. So especially in the insulation category, one EPD might tell you that a kilogram of this insulation has 10 kilograms of emissions associated with it. And this other one will tell you that a square meter at RSI 1 has a particular amount of, and the another one might give it to you in meters cubed. So what we've done in the tool is like all that crazy math so that you do get the same answer. So especially for insulation, you're getting the answer for the amount you would need to get to that R value. So, if it takes a third more cellulose than it does spray foam, that's been accounted for. So we've really tried to make sure that what you're seeing is a comparable result per the actual specifications that you've given.
Okay, thank you. So one person asked, can the tool be used for retrofits in addition to the new builds?
Yeah, absolutely. I mean, you just would use less of the tabs, but you're unlikely to be building a brand new foundation in a retrofit, so you might skip the footings tab altogether. But the sort of parameters you'd put in, the amount of, say, exterior wall you're dealing with. If you're changing out windows, you could use the Windows tab, roof insulation. So you would just use whatever parts of the tool apply to you. But on the user input sheet, you may not fill out everything because you may not be caring about all of the parameters.
Right. So that's a really good point. So when you're doing a retrofit, you're not modeling the current house. It's only the upgraded materials that are going into the house. Yeah, that's a really good distinction. So you'd be looking
at the parts of the building you're going to be changing,
right.
And you'd only account for those.
Right, because the other ones, the emissions they've already been spent,
Happened.
I guess
Yeah,
could
you
say.
can't really
Yes.
do anything about them anymore. They're in the atmosphere. Yeah.
That's right. Okay. A couple of other questions that came in were, does this platform have ratings on different continuous insulation products for the exterior of buildings?
Yep. So I was just showing you the cavity insulation part, but right underneath that, there's a continuous insulation part. So, basically, yeah, anything that you would sort of typically be applying to a residential building in Canada or North America, you'd find in the tool. So we tried to sort of break them into categories that made sense. So cavity insulation is its own section, and then continuous insulation is its own section, and that allows you, because you'd probably have different R values for each of those. So that allows you to kind of tune them separately by the parameters for your building.
Thank you. One last question. Let's see here. It says, surprised to see such low total GHG emissions for concrete products and such high total GHG emissions for sheet metal roofing. Are there lower GHG sheet metal options, perhaps based on area of production and input energy intensity?
Yeah, so there's a couple parts there. So GHG emissions for concrete are huge. If the concrete industry was a country, it would be the third biggest emitter on the planet. So I'm not sure where the notion that it's small is getting to. We just finished a study for Nelson, BC, where we looked at 35 new homes, and concrete was 35% on average of the total emissions for all of those homes. It's the biggest piece of the pie in almost every building we look at. So it's not low. What you might see when you look at the numbers is it's low per weight. So, if you look at kilograms of emissions per kilogram of concrete, you'd be like, oh, that's a pretty low number. But then when you think about how many kilograms of concrete go into a building, the number goes up fast. And likewise with steel, a metal roof has a fairly comparable carbon footprint to other types of roofing. Metal itself has a really high carbon footprint, but there's not a lot of it in a metal roof. Metal roofing is one of the areas in the tool that has quite a few options. Quite a few manufacturers and manufacturer groups have done EPDs. Again, it's nowhere near all of them, but you'll see like quite different results. As much as 30-40% in the amount of emissions difference between different manufacturers. And again, that'll have to do with their supply chains and their own in-house processes and energy use. But that's where the more EPDs we get, the better you'll be able to make those choices.
Exactly. And on the concrete, like I've seen where with using the tool where, if you've got slab on grade, you just have a considerably lesser a volume of concrete. So therefore that number is lower, or you may be just looking at one component within the spreadsheet. Oh, it looks like a couple more questions just popped
in. And so, Lindsay's just clarifying. Yeah, that
yes,
the example I showed you was for a building that worked very hard to have very little concrete in it. So that was a surprisingly and encouragingly low number, but usually it is much higher.
Right. Okay. Got it. And Lindsay, thank you so much for clarifying on that. So the last question that just came in is, I'm assuming that as EPDs for other materials not in the tool now will be updated moving forward. So will the tool be updated as new EPDs come on stream?
Yeah. We still have to kind of set a schedule. Are we going to do that once a year, every 6 months, when a certain number of EPDs show up? But absolutely, because we're kind of right now, I think at the start of what's going to be a really steep curve in the number of EPDs coming out. So, we're going to obviously do our best to both in the categories we already have, diversify and include more, but also start to add more categories. I would really like to, I think the mechanical, electrical, plumbing side of things, I think we might be missing 30, 40, 50% of the picture by ignoring that. So, I'm really hoping that, the more data that comes out, the more we'll be able to include in the tool.
Yeah, exactly. It is such a significant component in the home. So hopefully we can get some encouragement from from the industries to participate. In fact, sort of kind of related, a question just popped up and it said, are governments doing anything to discourage the production of high emitting materials and encourage production of low emitting materials? So that's a question. And I would say, is there any, to expand on that, is there any push by legislation to get more EPDs?
Not directly. The I believe it's called the Greening Government Report that the federal government put out a while ago, said that in either 2022 or 2023, government construction projects are going to require EPDs in order for products to be able to be used in government buildings. And I think that's the first thing I've seen in Canada that's not, it doesn't make every manufacturer do an EPD, but it means that, well, if you don't, none of your material can be procured on any federal projects. So I think that's a really good start. I think there's, obviously lots more that could be done. I think in particular, I hear from small companies that really struggle with that. Like they know that they have a material with a really great low carbon footprint, but they're a small company or a startup and they can't necessarily afford the EPD up front. I think, it would be really great to see some, assistance for things like that. In the US, there are a number of states now that have passed buy clean bills that are similar in terms of for government procurement, an EPD is required and it has to be less than the average, in the field and things like that. So there is, I think, some slow movement now, and I think we'll kind of hopefully see that really ramp up because I think everybody's kind of just over the last couple of years tuning into like how big an issue this is. And so, there's a bit of scrambling happening to figure out what to do about that.
And so on the question that was asked about what is government doing essentially to discourage the production of high emitting materials, I know that there was some action taken on the spray foam insulation, right? Are you aware of any work that the government is doing kind of on that front to reduce emissions in productions?
Yeah, I mean, that the sort of fluorocarbon things came from the Montreal Protocol. There's sort of, a phase out of different of those different chemicals. So it wasn't that there was a thing that said, hey, spray foam industry, you can't do it this way. There was generally, those chemicals are sort of being outlawed from, starting from the worst offenders and moving down. And there's, a progression of that has kind of been in the books for 15, 20 years. So that wasn't directly building materials, hey, you have to be lower emitting, but it's it's an example of how regulation could be used to kind of push things along, especially in the sectors that have the highest emissions.
There's a couple more questions, but I know that we're kind of getting short on time. So I wanted to throw it back to you to see if you had any more to continue on with, then we can do that. Otherwise, we could answer some more questions.
Yeah, I do. And I think I only have a few minutes, so I'll try to get to this part. And then if there's time for questions at the end, I'll try to pick those ones up again. So what this next section is, it's short because it's a bit of a teaser for the next one. But this is a look at what do we see, so now we've got this tool, we can look at buildings through this lens. What do we actually find? We did this report with NRCan, came out a month or two ago, where we looked at their 3 housing archetypes at 3 energy code tiers in 5 cities. And then we applied 4 material scenarios to those buildings. So this is kind of the first comprehensive national data set of model buildings, and the results were really interesting. I'm going to go quickly here because everybody knows the energy story, that a tier 3 building on gas has fairly high operational emissions. If you move it up to tier 4, it goes down. If you make it all electric, at least in Ontario, and keep it at tier 3, it goes down even more. If you make it a tier 5 all electric building, you've come close to getting the operating emissions extremely low. And so this NRCan study was to figure out, well, up front, this is only on operations. What is this upfront piece, and what does it look like? And I'll show you quickly what it looked like. So this is for a 2-story home, the 2-story NRCan archetype. that the worst emitting version that we made in the study had almost 140 tons of emissions associated with the materials. So if you got that building down to a really low carbon footprint on the operational side, you can see that the materials represent, the vast majority of that building's emissions in the decades coming up. And in fact, it'll take 315 years of operating that building before the operational emissions have equaled these upfront material emissions. The next model we did was sort of a more moderate version. It ended up having just over 30 tons of emissions associated with the materials. I would say this is somewhat representative of most, home typologies in Canada. But again, it's still the lion's share of the emissions over the next 20 years anyway, belong to the materials. It'll take 71 years for this building to have its operational emissions equal this upfront carbon footprint. The next model was super interesting because here we used materials that were widely available and code compliant, largely things like cellulose insulation. And this building ended up with a sort of net carbon storing footprint of just around 20 tons. So you can build and operate this building, and in 20 years, it'll still be a net store of carbon. And this is, as governments push to get to zero emissions by 2030, 2040, 2050, whatever the target happens to be, this suddenly starts saying, oh, like the home building industry could do that. Like we could actually make carbon storing buildings whose operations are low enough that the building remains a net store of carbon for a number of decades. So 45 years, this building would stay net carbon storing. And then we kind of did a best case scenario. What if you use the best materials for carbon storage? They're not necessarily common, they're not necessarily code compliant, but we know that you could use them. And here you're able to store over 80 tons. And now this building is net carbon storing for pretty close to 200 years. So that sort of gives you a range from these model buildings. We're also doing some studies of as-built homes. So, this was our NRCan results for a Toronto 2-story home. The worst case was 138 tons. The moderate case was 31 tons. And sort of the best conventional case was storing 20 tons. We're just getting towards the end of a study of 100 different homes that have been built in the last few years in the GTHA. And what we're finding so far is that for 2-story detached homes, 88 tons is the worst result, but 50 is the best. So what we're kind of seeing is that the modeling that we did for NRCan, the real life picture kind of fits right in the middle. The worst aren't as bad as we might predict, but the best are nowhere near as good as we would predict. So that study will be coming out in the early part of next year. And so, we really hope that that will kind of help show people what the emissions profile looks like of real as-built homes in this part of the world. And just quickly, one of the things I noticed, I'm glad somebody asked the question about the other categories in EPDs, the other impact categories, because one thing I noticed is that I sort of did a look where I said, well, let's look at the lowest carbon footprint material in every category, and then look at the other categories in EPDs. And what I realized is that the lowest carbon footprint also scored the best in all the other categories. So, a lot of these materials carry with them less toxicity, improved occupant health and safety, lower waste, and they can also sort of be sourced and made locally. So it's not, I'm very cognizant as a designer and builder myself of like not wanting just like this single lens where I make choices based on one metric, and meanwhile sort of really wreck things in other ways. So, in applying that lens here, what I found was, if I was choosing materials for a low carbon footprint, I was also choosing materials that lowered impacts in lots of other ways. And there, I think I ran that part fast, and so we have a few more questions. I hope that wasn't too fast, but I just wanted to give people a sense of, what those numbers mean. And I think what's really interesting is the crazy range that of results that you can get, from, because that modeling is of the exact same building. It's the same size, shape, R values, performance level, floor area. Like, it's literally the same set of plans, just with different materials thrown at it. So the fact that you can make a building that has either, hundreds of tons of emissions associated with it, or 100 tons of storage associated with it, or anywhere in between, it sort of points to the fact that, as a community, there's a lot we can do to really drive to lower emission buildings.
So that is great. And I'm really excited that our next session next week, you're going to dig into this report and talk about case studies as well, so we can expand on that. So thank you very much, Chris. Yeah, we've got a handful of questions here. So what we'll do is we'll start at the top. So how do you treat windows? They said, I can imagine finding numbers for glass, but frame materials vary widely. And does it matter percentage wise with respect to siding, insulation, et cetera?
Yeah, so practically speaking, the user of the tool defines the exterior wall area minus windows, and then says how much window area. So those two things are tracked separately. There are not a lot of EPDs for windows, like from window manufacturers right now. So this is the only place in the tool that we've done this. But for the window section, we kind of took EPDs for glass, for window glass, and took EPDs for different types of frame materials and kind of put them together to make our own figures. What's really interesting is that the difference between the carbon footprint of the frame materials, it's very small, partly because the materials have relatively similar carbon footprint, but more because you use, on a percentage basis, very little of the framing material versus glass. And glass is an incredibly high carbon footprint material. So almost all of the carbon footprint of a window is in its glass, it sets up one of those interesting things. That's where this tool is really helpful, because in moving, say, from a double pane window to a triple pane window, you're upping the carbon footprint of those windows by 33%, automatically. Is that trade-off in carbon footprint, does it pay off in terms of performance? That's the kind of thing that you can start to use this tool to extract, because you can make your hot model and see it with both double and triple pane windows, and you can make your material emissions model with double and triple pane windows and go either, oh, it's totally worth, taking the hit on carbon footprint for the triple pane windows, or, oh, no, it's not, I'll never make that back up. So I think, it's a great example of the way that the tool can be used.
Exactly. It really just goes to show the importance of being able to look at this from the full picture, which is, I know, what I had spoken about earlier, and what you've just kind of reinforced here. It says, is there a mention of what type of EPD the data is pulled from? So, for example, industry EPD, type 3 products specific, facility specific EPD. Do you handle data from each type of EPD differently?
We don't handle the data differently, but we, in the layout of the tool, we sort of try to make it clear what type of EPD it is. So if it's an industry standard, in the line describing it, it basically says that it's the industry standard. If it's a product specific, we actually name the manufacturer and the product, and they're sort of set up in a sort of hierarchy that hopefully makes that clear.
Thank you. Do you have plans to include tools for deep energy retrofits of existing homes where we're comparing high operational emissions from the before case to recladding, new windows, new insulation, et cetera?
Yeah, so I think this is the tool for doing that. And I think, this might be the highest value that the tool has. So, you can do your energy model on that deep energy retrofit and, have a sense of what the operational difference is that you're going to make in the emissions, and then you can run different material scenarios to get there, and then you'll have both pieces of that pie. So if you're going to save 10 tons a year, but you're going to put 100 tons of emissions in the atmosphere with the materials, then you get to weigh out, is that worth it? Like, does that feel like the right balance? Or maybe you can go, oh, I could get that 100 tons of material emissions down to 50, And now, I'm going to sort of come to a sort of, I'm going to be doing something better for the climate only 5 years out. But you may do those two analyses and go, oh, this is going to take 100 years, in sort of carbon payback time. This is not the strategy to be taking. I really hope that that's one of the main uses of the tool, because my biggest fear right now is governments are sort of cranking up spending on retrofits of buildings with no material lens at all. And I've seen from some of the models that I've done that quite often the scenario is we throw really high carbon materials like, spray foam insulation and new windows at a building, and we improve its energy efficiency by 25%. And like that, it'll be a decade, or it'll be decades, maybe centuries before we've done something good for the climate, and we don't have centuries to do something good for the climate. So, I really hope people in the retrofit space will start to use the tool to make sure that they're not having this unintended consequence of, we're trying to drive emissions down by retrofitting our buildings, but we could be driving them up by retrofitting them in a sort of unthoughtful way.
Well, exactly. And if a payback period is, say, 100 years, well, that building may not even be standing at that point. So,
or we may not have a livable climate in 100 years. Like we really have
that too.
That's why I really framed those graphs I did in a 20-year window, because honestly, if it's not better for the climate in 20 years, it's probably not something we should be doing, because we only have this sort of limited time to really drive it down. We can't be thinking of a century of carbon payback. It doesn't help. So
exactly. And so that's again something I had mentioned the last time, and just remind everyone, so that the Paris Agreement, the goal is to keep our emissions down so that we have less than 2 degrees C, ideally 1.5 degrees C of warming by about 2050. So in order to hit that, in that sort of net zero 2050 that we've been hearing everybody talk about, we need to, according to the United Nations, cut our emissions in half by 2030. So cut our emissions in half in the next 8 years. And that's a big undertaking that's going to take all of us kind of working really hard to get there. So now, I know we're a little bit over. There is one more question. So this all is being recorded. So if anybody needs to hop off, you can always watch this recording after. But I will ask this last question before we wrap up, if that's okay, Chris.
Sure. Although, if we want this is literally the question that the next session is set out to answer. So I could give a very quick and dirty answer here, and a little teaser that this is going to be the guts of the next one.
Perfect.
So, one interesting thing from the NRCan study is that we found zero correlation between cost and carbon footprint. So in other words, sometimes the highest cost material also had the highest carbon footprint. Sometimes the lowest cost had the lowest, but that could be flipped or anywhere in between. Like cost and carbon footprint had no correlation that we could see. So, I would say the standout from that study was something like cellulose insulation, where, it's a net carbon storing insulation. So it really, drastically alters the carbon footprint of a building. But it doesn't really, it's not in material costs, it's often less expensive than others, but like in installed cost, it's relatively comparable. So, that was one where you could really see that you could make a much lower carbon footprint building without incurring higher costs.
Okay, well, thank you so much, Chris. And so I'm really looking forward to, I know we're over, so we'll end it there, but I'm looking forward to our next session, which is November the 18th at 10:30 in the morning. And that's where you're going to dig deeper into these case studies and into your study. So thank you so much, Chris. Thank you so much, Lucas. And of course, to Enbridge, thank you all for your support and your contribution to this 4-part series. We'll see you guys next week. Be sure to register. Each one has a different link, so be sure to register for that. And when I sign off today, you will get a little pop-up for a Survey Monkey. Just fill that in. And afterwards, later on in the week, I'll send out all of the presentations as well as the link for the recording. So thank you again. And Chris, thank you. I'll see you next week.
Okay. Yep. Thanks, everyone.
Bye.
Thanks all.